Right. In 1 minute, I will start discussing stuff. That was Iranian contest. Cool. The contest wasn't bad for sure. Maybe a bit too easy for me. Like, I didn't need to think that much about problems, though. It was fine. One last thing before we start is, if you're interested in 3-person group classes, cost is $60 per hour, and then reach me via email. If you're not interested, well, still, I make a lot of free streams. I will leave that for a moment. Okay, 5 seconds. A little bit of self-promotion. All right, and let's go. First, problem A. I will mark it here next to my face, so it would be later easy to find. I will assume that you know the statement. So observation is that we always choose that allowed min or max at every vertex. Why is that? Because when you look at the final solution, the final assignment, if there is value in some vertex, and then there are neighbors. Let's consider vertex where you can choose anything in interval from 10 to 20, and in neighbors you chose values, say 5, 8, 12, 13, and 19. There's some set of values, and we think that this is the optimal tree. Then here's the thing. Once you choose the values at neighbors, then the function here is concave or convex, the one where it has minimum and it grows faster and faster. Actually, the fact that it's Bitonic is enough. So it's a well-known fact that if you want to minimize the sum of lengths, you need to choose the median of this. So median minimizes, and the further you go away from the median, the worse is the solution. So in interval 10, 20, in this case, 12 will be the best if you wanted to minimize, but if you want to maximize, it will be 10 or 20. And this observation is enough to solve the problem, because then it's dynamic programming on a tree. Every vertex, if you want to write it down as one global array, it will be dp of n by 2. For every vertex, there are two possible states. You chose the minimum allowed value or maximum allowed value, unimodal, I don't know, Bitonic, decreasing and then increasing. So at every vertex, if you chose minimum there, you want to know the optimal score for its subtree, and if you chose maximum, then you want to know the optimal score for the subtree. Then when you look at any vertex, you go through its children, you run DFS there to grab its DP values, and then for every child, we see that, well, if I'm, let's say, this vertex 10, 20, and then one of my child says, well, I can be of value 7, and then the total score in my subtree is 250, or I can be of value, say, 40, and then the total score is 260 or 240. Then you know, looking at just this one child, then my vertex, either it will be value 10, and then the score will be, well, I can choose between this. I have a difference of 3, 7 minus 10, that's 3, plus 250, that's 253, that's possible score. Or I can have score, if my child goes with this scenario, I will have score 240, plus the difference of 10 minus 40, that's 30, so 270. And I need to choose maximum out of those two, so in this case I choose 270. That's one possibility, and the other is I go with 20, and similarly I compute what's the score. It will be maximum of two values. And I need to go for children, and for each child decide if I want this scenario or this one. Like a moment ago, I went with maximum of 253 and 270. Complexity is linear. Right, it's just O of n. Also, this might be better for you, right? Yeah, this will be more convenient. It's just DFS. And code. I went with pairs where DFS returns a pair of long-longs. The long-longs, I think, are needed. Int is not enough, otherwise you have overflow. For me, DFS returned that pair of values. Moving on. Questions, chat? How to prove the complexity? DFS is linear. It visits every vertex only once. Time limit exceeded in Python. Sometimes organizers aren't that careful about whether Python passes or not. Problem B. In problem B, there are some conditions where they say that two intervals, one need to contain the other, or they need to be of the same length. Now I need a drawing, and sorry about that, but my drawing tablet is still a bit messed up, so I will have, how do I go about it? Yeah, so I will have some, I cannot stop drawing once I start drawing, so the drawing will not be perfect, but here's the thing. We start, let's say there are 6 nodes. This will be so ugly. Okay, let's do it differently. I will draw with my mouse, at least in this problem. 1, 2, 3, 4, 5, 6. Let's go with 8. The first point needs to be connected with something. If it's connected like that, then what we are left is just 6 remaining nodes, and it's not that this pair, this interval, will be in contradiction with anything else. It contains everything else inside, so everything else here, it just can be whatever. So from this we already know that dp of n, let's say that n is the number of nodes. That's dp of n minus 2 plus some stuff. dp of n minus 2 refers to how many ways we have to handle this. What else we can do? And this is a bit different from the statement. In statement they said that n is the half of the number of nodes. Alright, now what else can I do? I can, instead of this thing, I can make this to be the first connection. This is so annoying without my drawing pen. Let's try. This can be the first connection. And then what? We for sure will have one intersection. This guy needs to be connected with somebody. And then if they intersect, they need to be of the same length. And the only way to make this guy intersect and have the same length is that. Why did it disappear? Alright. And what we are left here inside is the remaining interval, the remaining nodes, n minus 4 of them. And you can keep going like that. By keep going like that, I mean, depending on the first connection of the first node, if it will be, let's say, connected with this guy, the third from the end, it will force some other connections. Let's actually see this, one last thing for us as an example of this first guy being connected to something. So if it's like that, we cannot have this connection. This is forbidden, because then those two intervals, one doesn't contain another and they don't have the same length. So instead we need to do it like that. And same about this node. It needs to be connected like this. And we have our n minus 6. So this thing below continues for some time, this formula. And I thought first that that's it, but that's not the only thing. That's the only thing we can use, because this could be done with prefix sums. So that's easy, but that's not the only possibility. Another possibility is that we will have some short interval. Still, I consider what is the connection of the first node. If the first node say this is the first node, this guy. If the first node is connected like that, then it doesn't provide any requirement. What requirement it provides about this guy? Well, something like that. And then everybody here, they don't intersect with that, so they need to have length of 3, because they don't contain this one. And it actually forces everything to have length 3, because if you draw this guy and continue drawing, then can we draw here interval of length 2? No, we can't, because this interval and this one on the right, they don't contain one another. So the fact that we here on the right start drawing things like this, it means that on the left also we need to do that. And then here I'm able to finish the drawing. But in this case, so if this first connection of first node versus somebody else, if it's short enough, then it forces everything to be made with this connection. And here it was an example where the length of connection was 3. Then here I have groups of 6 consecutive nodes such that they are connected to each other like this into pairs. And then this also needs to be 6. So what we have here is we can have this short connection of length 3 with a condition that n modulo of twice 3 is 0. Or in general, n the number of nodes modulo twice k must be 0, then it's okay to make all connections of length k. This is, well, n is always even. Actually, this n, it's double the value from the input. So if we actually say that n is half of the number of nodes, like the statement said, then it becomes this, which means we count the number of divisors of n. And it's the number of divisors of n plus whatever we counted here previously. This part we handle with prefix sums. Actually, if dp of n says what happens if n is half of the number of nodes, then it's that easy. Just prefix sum of all the dp values so far. And we need to, when printing, add the number of, when computing dp, the number of divisors of n. For that I run primesieve. So first with primesieve, always for every value like 5, actually not primesieve, for every value from 1 to n, let's say for value 6, I go through multiples and I increase their answer by 1. So I see 6, well 6 is divisor of 6, 12, 18 and so on. This way in n times log of n, we can count divisors for all numbers 1 through n. This is how, so this is the heaviest part of this is the bottleneck, because this thing is just linear. Let's see the code, some things will become more clear. What do I have? First I have this part where I iterate over every value, starting from 2 apparently. Why is that? Why shouldn't I start with 1? Maybe because it represents combining, I think 1 would represent combining a node with itself, and that's forbidden. So starting from 2, I go through all the multiples and I increase by 1. Now dp stores counts of number of divisors for every number. If I print it now, say cout dp of 100, it would print the number of divisors of 100, not counting divisor 1. And then I go from 1 to n, and always to dp of I add prefix sum, where pref is just the sum of all values dp so far. And that's it. Time for questions. I'm angry at myself about this runtime error because I lost 50 points for some stupid reason. Well, almost every wrong submission is stupid reason, right? And it costed me like 4 places, which is actually very important in the top. I don't see questions, so we're moving on. Problem C. Problem C. Also, if you want to later watch my screencast, it should be uploaded here. Yeah, it's this thing on Eric22 channel. I should remove hash from here because then the title becomes stupidly formatted. And during the contest I commented, at least in the first half. So the complexity of B was n log n. Now we're moving on to C. We need to find a click where a click is something very specially defined. For that we need a drawing. It boils down to this thing. In the first tree, the chosen vertices, they need to be ancestors of one another. So if this is the tree, the first tree, then one thing that you can choose is, let's say, this guy, this one, and this one. This is a valid choice. They are all connected. Then what about the second tree? In the second tree, they need to be not ancestors of one another. One way to say what they are, then, it's cousins. They are cousins to one another, like siblings or further away siblings, not necessarily on the same level. Let's say this is the tree. One valid choice is then, say, this guy, this one, but doesn't need to be a leaf, this. This is okay. Nothing is ancestor of another vertex. Then if those three vertices correspond to those three, then this is a valid choice of three vertices. We need to choose as many vertices as possible. And now, if I chose this guy, I couldn't choose this one. All right. How to approach it? I will run DFS on the first tree. DFS has this nice property that in DFS always, when you're in some vertex, you can store information about the path from the root. For example, in a vector, in some kind of stack. In DFS, it's easy to store information about path from the current vertex to the root. And I will indeed store it. And always when I'm in some vertex, my goal is to know what's the best set, what's the best choice of vertices in this path. Then when I go down in DFS, I just need to consider adding one new vertex in some greedy way. But what about the second tree? Whenever I look at some vertex in the first tree, I see where it is in the second tree and I need to understand something about it. In particular, let's try to understand, say, how do I do that? No, I know. Let's say this vertex isn't chosen yet. And now I look at this new vertex and I say, maybe I'm allowed to also take it. For now I took two vertices and I want to choose the third one. So now my set will be of size 3. And then I can look at its position in the other tree, and I need to very efficiently say if this new yellow vertex, if it's ancestor or descendant, or some of the green vertices. This check alone is not enough, because sometimes it's actually optimal to replace vertices, but let's start with this. So what we need to efficiently check, and I will write it down, efficiently check if new yellow vertex is ancestor or descendant of any chosen green vertex. And this is check we do in the second tree. In the second tree, check if the new yellow vertex is ancestor or descendant or of any of already chosen green vertices. It would be very inefficient to, for example, run DFS. Without running DFS, how to quickly, even for two vertices, check if one is ancestor of the other? We can do that with pre- and post-order ranges. What we do is we do DFS traversal first as pre-processing. DFS traversal on the second tree, then we store pre-order and post-order for every vertex. It is a range, and then one vertex is ancestor of the other if one range contains another. Now, if you don't know that, you need to read about DFS traversal and pre-post order. So now every node, it corresponds to some interval, where this interval corresponding to this vertex, it will contain interval corresponding to this vertex. So I could iterate over green vertices that are in the set right now, and for each of them check if they contain yellow interval or yellow contains them. That's quadratic, but for example, if the answer was small, so if always the set was very small, then it would be fast enough. This is now linear time of DFS times every time we need this efficient check. Right now we are able to iterate over the set of green chosen vertices and check those interval properties. Before we move to faster implementation of that, for which we will need some data structure like a segment tree, actually I will use a set, but maybe segment tree I think also would be fine. We will say what's actually the correct but slow solution, because it isn't enough to check this, and if that's allowed, then insert a new vertex. Sometimes we should replace, and we should replace in situations like this one. Let's say that so far we chose this green vertex and this one, and now we are looking at this yellow. I cannot insert yellow because it doesn't work with this green, they are ancestors of one another. But what I should do is I should erase this green and replace it with this yellow, because this yellow, it allows more. Later maybe I will encounter those vertices and then they are fine. Kind of, the lower the vertex is, the better for me, because it forbids less stuff. If new yellow vertex is descendant, so something in subtree, it's below something green, then it replaces it. And this is what would happen if here this was green a moment ago. Right. So in this check, not only we check if something is ancestor descendant, but also if something green is ancestor of yellow, like was the case here, then we need to find this guy. Also, fortunately, only one green can be ancestor of yellow. This situation is impossible because we know that so far greens were a valid set. So this situation of like parent-child or anything like that is not allowed, but maybe this is allowed. And if we actually replace green with yellow, then we're good. Just we need to remember that this is all in DFS. So when we go to a child and we go further down in DFS, we maybe replace one vertex with another, but later when we come back, we need to roll this back. Before I continue, I will just show roughly what I did in code for that. This is C, not D. In code, in DFS, I have some variable for what I removed. I found a green guy to remove. I continue further down in DFS, it's here, and then after that I need to roll back, and here I cancel this removal, I roll it back. But now we need to talk about how actually to handle this efficiently to then understand what will be the rollbacks. Right. We have intervals, they are disjoint. Green stuff, those are disjoint intervals because nothing is ancestor of one another. For example, maybe greens, they form like something is interval 2-6, something else is interval 8-8, and in such a sequence of pairs, we need to now say for a new, let's say now yellow is 7-9, and we need to quickly check. This example doesn't correspond to that tree, by the way, and also we can focus on a new slide. Maybe this is a longer sequence. But what's important is, in this sequence, there are no intersections between intervals. Maybe like that. Now we have this yellow, and we need to know if yellow contains something from here. If this is sorted, we could use binary search, but we insert and erase new stuff. So to be able to use binary search, let's say that this is a set of pairs. Then I can use lower bound on this pair to see the next pair with value 7 or greater. With lower bound on this set, I will find this one, and this is the candidate to be contained in yellow. So the logic for me in C++ was like that. Iterator it is set.lower bound of yellow. If yellow contains it, then do something. And also if not it contains yellow, this is not really that. How to check if something from this contains yellow? Well, the candidate is something with first value a bit smaller than 7. So that's actually this iterator -1. So you can write it -1. This will not compile, I think. Previous it works in C++. This is candidate who contains yellow. By the way, function contains, it just gets to pairs and checks if one contains the other as an interval. Yeah, so that's what I do, and I store that in a set. Then all the operations can be done in logarithmic time, and the full thing is n log n. And that's it. I didn't here fully prove the correctness, why it's just enough to swap like that and then that's it, nothing else. But if you think about it, it's intuitive, it's the best you can do. To summarize, by the way, the idea for this, when I run DFS for this, always when I miss a vertex, it's easy for me to store information about path from the root to the current vertex. And for this, I want to know the best set. So set with most vertices, and in case of ties, I prefer vertices that are more to the bottom, because they, I mean more to the bottom in the second tree, so they wouldn't forbid a lot of other vertices to take them later. And always, when I see a new vertex in the second tree, I check if I can just add it to a set. If yes, then I add it. If no, then I also consider replacing. If yellow is below something green, so yellow is contained by green, then I replace. But then when I'm exiting from this vertex, I need to roll this back, which is easy. I just remember what element I erased from a set, what I inserted, and I erase the inserted, insert the erased. Did I study computer science? Yes, I did. Time for questions, if there are any, and then we move to problem D. System testing done. If this is final, then I'm LGM again. Looks like that. But again, I had in the wrong submission, 50 points, I would be 12th instead of 15th. I thought that 4 spots I missed, but apparently only 3. Oh, it's not that bad. So I would be 12th instead of 15th if without that wrong submission. Then I shouldn't complain. Problem D. The statement is very complicated. And also I don't know if I have the intended solution. My complexity is n-cubic. The space complexity, by the way, what space complexity do I have? I think quadratic. I have nm, so or n-cubic manga. So I have 600 cubic. I don't think that 600 then times cubic times log will pass. Can it pass? I can say a little bit about the statement. There are n cities. This will not be the very beautiful drawing, but whatever. And there are moving edges. From every vertex there is at least one edge. Like, as I said, my drawing tablet is a bit broken. Let's say edge from 1 is initially like this, and it has some cost. Let's say here there is a cost of 10 of traversing this edge. Here's the unusual thing. After 1 second, the target city changes by 1 to the right. So after 1 second, the edge will be from 1 to 4 with the same cost of 10. After 1 second then, this edge will be from 1 to 0, again of cost 10. Then from 1 to 1, which is a useless edge, because you can stay in a city anyway, so never use an edge to itself. Then from 1 to 2, and so on. After full 5 seconds, assuming that n is equal to 5, edge will be just like at the beginning, from 1 to 3 of cost 10. And the process continues forever. Given edges and cities, we need to, for every pair of cities, we need to find the shortest path, length of the shortest path, assuming that we start at second 0. Stop spamming, or you will be banned forever. Yes, we need to do that. And whenever some process happens modulo n, it makes sense to care about the current time modulo n. Right? It doesn't matter that much if n is 5. It doesn't matter that much if the current time is 2 or the current time is 102 or 107. The graph looks the same. So there is no difference between them, and the remaining strategy will be the same. From this immediately I got the idea that maybe I should compute n cubic values, where for every pair of cities what's the shortest path, assuming that I start at this second, where s is actually the remainder modulo n, so it satisfies this. And I still think that this is easy to compute in n cubic, but the issue is that this is n cubic space complexity. And I hope that it will pass, but well, then I grabbed calculator, and 6 cubed, that's 216 or so, then times 10 to 6, that many ins, it's like 850, 860 megabytes, while the memory limit was 250. Then I thought that maybe shorts will be enough if I do some tricks, but it's still for 3.0. Then I thought maybe chars will be enough if I do enough tricks, but I think chars would work if n was up to like 130. Then even though costs were big, the cost, like here 10, it could be up to billion, I knew how to get rid of that big cost with some observation. Still, this wasn't promising. It was n cubic, but space usage was too big. So I scrapped this idea, and instead I went with BFS/Dijkstra from every node. My reasoning was that then the memory usage will be better. I will not remember for all the pairs for every for every time remainder, and instead I will just know distances for all the cities. Of course, Dijkstra seems better because there are some costs, but I don't want to get n cubic times log. I want to I aim for n cubic without logarithm, so Dijkstra is then not viable. But there are many cases of Dijkstra where actually it doesn't have a logarithm. So yeah, this seems promising. Or we can also maybe think about it as BFS with edges of small costs if we do some observations. Dijkstra for edges of small costs can be done a little bit like BFS. Alright, that's the plan. What exactly can we do? When we start from city 0, for every other city I will compute when is the first time I can be there. All right, seems promising. What happens there? In Dijkstra, when I'm in node V at time t, what should I do? I should most likely consider all the edges going out of this node V. And I know that at time t they are in different places. But let's say I consider using all those edges. So in Dijkstra I meet this pair, and then for all edges of type from V to some new vertex, let's say W, from V to W, I see that I can get to W with at some time. But maybe it's better to wait at this current city for at most n seconds, for edges to change a little bit. Then for all the edges, maybe I should also iterate over the amount of time I wait from 0 to n minus 1, and then it will be too slow. Because right now, the current complexity here is the following. For every starting city, I run Dijkstra, right? Dijkstra. And Dijkstra then encounters a lot of pairs like this. For every node it will be encountered once, so my complexity is n times n because there can be n edges going out of V. This is already n cubic and I cannot iterate over anything else. This word Dijkstra just means that whatever happens here is Dijkstra, it's not really a for loop. Well, actually Dijkstra means that we iterate over that in some kind of loop. So how to not iterate over the waiting time? Here's the trick I used. What was the trick I used? Vt implies v plus 1 t plus 1. That's the trick. I also added fake edges, and fake edges, and then I said edges don't move anymore. What is this? Well, let's think. If we start from 1, and there is edge of cost 10 finishing here, it means that I can be at node 3 at time 10. Sure. I can also wait 1 second, and then this edge will go to node 4, and I would be at node 4 at time 11. Instead of saying that this yellow edge moves, I will say that when I'm at this pair, node 3 time 10, I can pretend that the previous edge I used, actually I wait 1 more second with that, so I jump from node 3 to node 4 by using time of 1 second. So I add those edges. This just means that for every V, I pretend that there is edge from V to V plus 1 of cost 1. And this edge is always there, with one exception. The only exception is the starting city. I need somehow in my Dijkstra forbid the scenario where, initially I'm at starting node. Let's say that I start from node 1 at time 0. Then I don't want my trick to think, to make my program think that I'm in starting city 1 at time 0. I don't want to say that at node 2 I can be at time 1. No, this is bad. I don't want that. And you might say that then let's just not consider going from starting city to the right by 1. And maybe that's enough. I wonder if it's valid to travel some time and then get back here. I don't think so. I made a complicated hack for this. Like later in my Dijkstra, after I consider those edges starting from node 1, later I override this time to be infinity. So then somebody else will see that I can enter node 1 and I have something like, let's say this. where I know that I can enter that node after 25 seconds, and then I can enter node 2 after 26 seconds. I don't know if that's necessary. Maybe there is some easier method for this. I don't know. All right. So this is what we do. We use the trick in order to just iterate over current edges, to say that right now I'm using an edge. It's not that I need to wait some more time. And we are careful with this trick not to imply that if we start at node 1, then at node 2 we can be after 1 second. And to avoid logarithmic Dijkstra, in dense graphs in general, every time you need to iterate over all nodes to find the smallest one. That's a general thing you should know. Dijkstra is generally m times log of n, or it's n squared plus m. You can choose one of those. This is with priority queue, and this is with always to find the next city with shortest distance from the start. You iterate over all the cities. And then m is always, m cannot exceed n squared, so it's just this. Priority queue, just no priority key and only for loops. Priority queue, you write yourself, is faster than O of m Dijkstra? What, really? But how to implement priority queue fast yourself? With heaps or something else? Is this Fenwick tree? This is indeed very fast. I wonder if you really trigger n cubic times operation on this struct. You can... I'm interested in this. I don't want to do the whole thing, but something like that. Every time you run this logarithmic operation, can you do something like this in a global variable, and then at the end initial equal to 0, and at the end of main, can you do something like this? Operations assert that it doesn't exceed, let's say, 600 times 600 times 600 divided by, let's say, 10. With this, you can binary search what's actually the constant next to 600 cubic times logarithm. I wonder if really 600 cubic times you have logarithm, because this is surprisingly low time. Can you do this and binary search actually in the... When you submit this, if you get accepted, it means that the condition is satisfied for all the tests. So here, if you get accepted with this, it means that indeed you never exceed 600 cubic divided by 10 operations. If you get runtime error, then, well, try 5, and this way you can binary search. If you can tell us in a few minutes, that would be nice. But by the way, thanks for the insight that this was possible and it's so fast here. It's faster than my solution. I think my solution was 1.5 seconds. For D, yeah, 1.8. By the way, I did some more unnecessary stuff. I spent a lot of time on this problem, and I thought that I need one more observation, but this is unnecessary. Unnecessary, I made all distances to be up to n. Like distances from the start, or up to twice n, I think. N. I thought that I needed for the sake of space or something else, and I overcomplicated the solution. I will not even show you my code. How did I achieve this? So how did I get rid of big costs? Well, I observed something like that. For the starting city, if you find the smallest edge coming out of this city initially. Let's say that its value is 100. Then here's an observation. All the distance, because in particular you can wait here at most n seconds, and you can jump here with cost 101, you can jump here with cost 102, 103, 104, 105. Then observation is that all distances from the starting city are from 100 to 100 plus n. I don't know why I'm typing this, drawing this instead of typing. Answers are in 100 to 105, or 100 plus n. So what I did is I changed this to 1, and maybe I will write down actually. Let x be minimum cost of edge going out of the starting vertex. Decrease all the initial edges by x. All edges going out of start by x minus 1. For some reason I didn't want to get cost 0 because that's bad for Dijkstra. Dijkstra is then more complicated to implement. So I did this, and then this 100 would change to 1. If there was some other edge with value 110, it would change to 11. Then all the paths from the starting city I decreased exactly by that much. Then run Dijkstra or whatever. Actually, I ran BFS. I didn't use Dijkstra. And then print answer plus x minus 1. This is what I did, because with this extra step I guaranteed that the answers are from 1 to n plus 1, which helps. You can then run BFS. But this is unnecessary, so I only wasted time. What does LGM mean? Legendary Grandmaster. Oh, the rating is out. Yay, hooray. That's LGM for the 5th time. Great. And if I was scared and weak, I would just stop participating. But if you reach some rating and stop participating, or you're scared, then because you don't participate, you will just slowly get worse and worse. So that's a very bad strategy. I don't recommend stopping participating whenever you reach some good rating. Also, some people, they create new accounts, which is forbidden in Codeforces and very unfair to others. You steal rating and you just make the leaderboard skewed. So I'm going to still participate. Maybe I will get some kind of record for the number of times I reach LGM. That would be nice. I wonder what's currently the biggest number of changes from below 3,000 to above 3,000. It cannot be that far away. Alright, so we discussed D. You see that indeed I iterate over edges going out of the starting city. I find the minimum, I then subtract 1, and I wanted the graph to look the same as the initial graph, so also I made it to be divisible by n. So I decreased it down to something divisible by n, and then the distances are actually from 0 to 2n, or to 3n, something like that, because of this extra hack. And actually adding this just before the submit, it made this part of code incorrect, because somewhere here I actually assumed that distances are very small. They are up to n, not up to 2n, and hence wrong submission. And the complexity is this, and space, I believe, well, you need to keep the edges so you can do n square time the space. Decay to rating, so people can just see on their score. What happens when you open a rating tab is that this shows people who participated in past 6 months. If you want to see all the people, you will hit here. So the only thing to prevent you to stop participating is that after 6 months you will disappear from the leaderboard. you will be here, and for example the number of Nutellas here is 48, number of Nutellas participating in past 6 months is 48. I think that's a bug. Normally it's not like this. There should be people who are in rating all but not in rating. Rating all doesn't work? Yeah, okay. It's not a bug. Doesn't show inactive users. Has been like that for more than a year. Appears in the end. What? Ahmed, I didn't understand. Tips for you. I don't have general tips about becoming a developer. Last problem. After solving E, I actually gave up and I went to eat something because I was very hungry, and I'm a bit angry at myself because later it turned out that some people solved F in like half an hour. Here the time is half an hour, 35 minutes, 30 minutes. Of course, maybe they thought about this before solving E, but F seems doable. I was just, after I solved E, the situation with F was that I saw that some people solved F after 1 hour, and there only 2 people solved it. I had 40 minutes left, I was hungry, and also I wanted to set up the stream. But I should have fought for F. Log n part triggers n cubic times actually. Okay, so really this segment tree is very fast. We have like more than billion operations, right? Huh. Surprising. Maybe for a moment still I will change this to D because we're talking about D. I'm surprised that here n cubic times logarithm is fine, because n cubic is 200 million multiplied by logarithm. That's, well, oh, a logarithm is very small. It's not logarithm of million, or it's logarithm of this, and that's only 9. 9 is, okay, I see. So now, whenever, and now I understand why it doesn't change that much. Whenever you say that you have this complexity, actually the number of operations you have is maybe this times 10. You need to look at the bottleneck of your code, and you have a few lines, each with few tokens, and maybe you will have here 10 operations in total. It's simplification, but let's say it's that. Now if you add n cubic times log of n, where log is just 9 in this case, or 10, and now multiplied by how many times you do operations in this bottleneck. But the bottleneck for segment tree, it will be just one line. It will be very simple, like divide id by 2, which is very fast, and take value from some position of the array. Also the array, the segment tree will be all in cache. Segment tree will be of size 1000, it will fit in cache. So this is times fast, and this is times slow. Let's say for reference that this is 15, and this fast is 3. Let's say 3 operations we need inside the segment tree. So segment tree, let's say, does exactly log of n times 3 operations per every function call. Well, this is, let's say, 15, because you have 3 for loops, and inside you have few lines, in total 15 operations. Well then, this is not significantly bigger than that. That's, if we just compute 3 times 9, it's 27, 2 times slower. This was, of course, a rough estimate, but usually we think that logarithm is 20 times slower, because it's log of million or 100,000. Here it's like 2 times slower, maybe. That explains a lot. Now we can move to E. Thank you, Mango, again for checking this. I learned something. Or maybe I will be more careful in the future not to discard the idea of logarithm. Why very strong recently? Am I very strong recently? Okay, so everything I said in the past minutes is irrelevant. Then I believe you compared versus n cubic, and for very small tests it was triggered. Yeah, I can believe that for n equal to 2, maybe you will trigger almost n cubic or something like that. Then theoretically, maybe there are tests where your solution is almost 10 times slower. I believe that. But still, what I described explains why the difference isn't 20-fold. It's like I estimate it as twice slower. We don't know exactly. It's very hard to estimate the constant factor. But if my solution was 1.5 seconds, I would expect the times logarithm solution to be at least 3 seconds. But also maybe it's 10 seconds if there are strong tests. My solution, I think, is quite independent on tests. So it's not random test will be kind of a max test, I think. Now moving on. Best way to become good at programming? Practice. Nothing else. You can read this link if you care about competitive programming. Now, last problem, E. All the library and headers. Headers, just this single line, bits. For this, you don't need it. Don't use it. You're fine without it. This was the hardest problem, and there are conditions, and I needed to guess what they are equivalent to, and I spent some time on piece of paper until I got 31 for the second test on piece of paper. Once I did that, I assumed that this is correct. I implemented that in quadratic time first. Then I improved that quite easily to linear, but then it didn't agree here, and for half an hour I kept debugging and fixing my solution. So let's see what kind of trees, how they are called? Unordered trees? Unlabeled. We need to count unlabeled directed trees that satisfy something. The most basic kind of thing we should count is a tree where there is a vertex, starting vertex. There are some edges going out of it, and from them there are some edges going out of them. Also, maybe from some vertex nothing comes out, like this. And conditions are, there are two conditions. First is that longest path is of length exactly n. Second condition is that every degree at most 3. From the starting node there can be 3 edges, but from every other node, because there is one edge going in, there can be at most 2 edges going out. Those two conditions, and this can be done in linear DP. Maybe it's best to do something like that, where dp of n d is number of trees of length n. By this I mean the longest path is of length n, and degree of root is equal to d. Like this thing would be represented by length 1, and degree of the root is this first guy, is 2. Depending on your implementation, maybe you want to have here length up to n. because then you can say that dp of n, let's say 3, that's almost this, dp of n minus 1, whatever. When I put a question mark, I don't care how many, but you can have at most 2, right? So this should say 0 or 1 or 2. Times this, times that. When I say this, it actually means that I should sum up dp of n minus 1, 0, plus dp of n minus 1, 1, dp of n minus 1, 2. If I want, starting from here, want to have length at most n, then starting from here I want to have length at most n minus 1. This guy's degree to the right must be at most 2. So yeah, this works. But we don't count, this would work if we counted labeled trees, maybe with some binomial coefficients too. But we don't. We count unlabeled, and we don't want to double count stuff. If there is, let's say, this tree, we don't want to double count it with this tree. Those two, they shouldn't be counted separately. And they are the same because starting from this guy, it has the same children, just swapped. So actually this shouldn't be product. It should be something else. When you have those three values, actually it's the same value. Let's say for simplicity that this is x. Then a moment ago we had this thing. But this is incorrect because of what I said here. We overcount stuff. Actually what we should say is x choose 3. We choose 3 different types out of them, and every child will be of one of those 3 chosen types. Either we do that, or we choose 2 types, let's say types A and B, and then 2 children will be of type A, like this, or 2 children will be of type B. So there are 2 ways then to distribute types into children. Plus, we can just out of x types choose 1 and say all 3 children should be like that. This is really the formula, where C stands for binomial coefficients. This says x choose 3. You know, just x times x minus 1 times x minus 2 divided by 6 modulo mod. If you use int 128, then exactly this line will work. And then you don't need modular inverse. I will leave it, I guess. Alright, this is how we can count trees of length at most n. At the end, when printing the answer, we would need to print dp of n, well, whatever, minus dp of n minus 1, whatever. Those are trees of length at most n minus 1. The difference will be trees of length at most exactly n. Exactly n. But that's not the answer yet. For now, let's say this, but we will need to modify this a little bit. We were also asked to count the opposite kind of trees, where there is the root and then edges go in the root. So exactly the same, but reversed. The number of those is the same, so I will just multiply this answer by 2. But the path, just path of length n, will be counted in both this kind of trees and this kind of trees. So I need this minus 1. And I first thought that I'm done, that this is the solution. Quite easy linear time. But I was wrong for bigger test. For n equal to 2, I got the correct answer 31, but then I failed the bigger test. Because there are also trees that look like this, where there is, you can say there is a path, and there are extra edges going here. Well, no, then degree would be too big. let's say like this, and then from the right part of the drawing there can be edges growing to the right. So this is possible, where some kind of prefix of the graph is one type of tree going inside this this node. Suffix is the opposite. But no, this is something we already computed, the number of trees like that. So it seems to be that we need to add up. If we, like this said, let's say that this is how we can compute answer of n. This is the number, or maybe answer of n, and let's forget about this line completely. Answer of n is the number of trees like this, of length n. Maybe we should actually carry then here what exactly degree we want, because we want degree 2, not degree 3. That's an implementation detail. And then here, what we can have is, let's say that n is 5. Then, for example, I can have here 3 of length 2 and 3 of length 2. So I can have, I should say answer of 2 times answer of 2, but also on the left I can have a 3 of length 1 and here a 3 of length 2, and many other examples. In general, if there is a path, some prefix will be 3 of this type, some suffix will be 3 of this type. So it seems that what we should do, actually, it's not hard to do it faster than just with brute force, but maybe we should just do this. For I in 1 to n, for j in 1 to n, if I plus j doesn't exceed n minus 1, then I can fit those two trees. Total answer to print times equal plus equal answer of I times answer of j, where those are the number of trees that here I can have on the left and on the right. I is the length of this tree on the left. I will actually scroll this to the bottom. I is the length of this tree on the left. J is the length of this tree. You can, that's not hard to speed this up to linear time. You can use prefix sums on answer array. But the last issue is again some kind of double counting. To not double count, you should guarantee that when you say the tree grows out of this guy, let's say, let's see how we double count. We double count what? Let's say this tree. Right now this tree, if only it has those extra edges, it will be counted as this kind of tree, this kind of tree, this kind of tree. That's bad. Instead, when saying that this will be the special, branching tree on the left, I want to guarantee that this guy has at least 2 children, actually exactly 2 children. So answer of I, it should mean the number of here trees where the degree of the root is 2. This just affects slightly what actually you need to do here, and nothing more. So answer of I should be the number of here trees of length I, such that the root has 2 children. Like here, this is the root, 2 children, and then whatever happens here. So we have this part, you can speed this up to linear time with prefix sums, and also still you have this thing where twice you get the normal dp minus 1 to just count tree like this and the opposite kind of tree. That's it, O of n in total. It's in nobody is listening. I think there are people who are interested in solution for E. Where do I live? Warsaw. If you become my neighbor, please don't be loud during my streams. Alright, we are done, and I need to fix my drawing tablet because this is annoying. I didn't solve f, I didn't even try to solve f. The statement looked convoluted. I didn't try, and I should have. Same thing. This person also made the observation about distances being in some range, and we both did some unnecessary stuff. Well, what can we do? By the way, if you need my submissions, go to my profile in Codeforces, open my submissions, and then you will have a list of my submissions. So I don't need to upload them to GitHub or anything like that. Not a fan of counting problems where there's fundamentally zero computer science involved. I agree that it's better to actually use some algorithms. The code for E was trivial. You didn't use any algo knowledge. You needed to understand DP, I guess. Linka tree, that's an overkill. I said exactly, yeah, so that's my solution is the same. All right. Any questions? Ratism? Yes, this is ratism, but it's also logic and statistics. More often, somebody strong rated will write a good comment, or you can think about it differently. If somebody writes good comments about problems, or like provides an interesting solution, they usually get better rating. You can think about it this way. So if I want to get, I don't know, if I want to read a book, let's say like, you know, Game of Thrones or whatever, some kind of book, I usually read books made by millionaires, but it's not that they are millionaires so I read their book. They are millionaire because they write a good book, right? So it's not monism. It's not that I prefer, let's say, books, normal books written by people who have a lot of money, because the money actually comes from writing books. So here it's the same. It's not implication just in one direction, where I see that somebody has big rating, so only because of that I read comments. Actually, it's correlated both ways. If somebody writes good comments, then their rating becomes better in time. Mad at yourself for not doing good when you could have? It's normal. I don't know if it's good, Gupta, but it's normal to be mad at yourself. I'm even mad at myself for this wrong submission in D, because it was so stupid. Popular and rich does not mean good quality? Sure, I agree. It wasn't a perfect example, but I think you get the idea of what I tried to convey, what was the message. I think this kind of block is unnecessary when I got LGM for the fifth time. Alright, thank you all for watching. Consider joining the Discord server if you like watching my streams. See you in 2 days. I will do on Tuesday at in 1 day. So tomorrow, Tuesday, hard at coder problem solving. But also there is this calendar you can follow. Right, thank you for watching, bye bye. And also I'm very happy about my new rating.